Okay, welcome to Unit 4, Conservation of Energy, Lesson number 5, the Conservation of Mechanical Energy, and this is example number 2 out of 3. In this question, we have ourselves a cart, and this cart is on sort of this multi-leveled pathway here, and the question is asking us to determine what the velocity of our cart is at point C here. So this cart is going to be rolling down this hill, scooting across here and rolling back up. And we want to figure out how fast this cart is going when it's on this final platform. Alright, so we're going to be breaking into the conservation of mechanical energy formula again. Before we get going, I want to make a note that this middle stage of the platform here, because we're dealing just with energy before and energy after, at no point does this cart have a different value of energy. Therefore, we're not going to be doing any calculations in this middle bit. Hopefully, as we start solving, if you don't understand that now, that will make sense soon. But there's no friction, no nothing. This middle bit is just here to maybe confuse you a little bit. Or to, maybe not necessarily to confuse you, but to prove a point. So let's jump into this and see where it takes us. Before we get going, I'd always generally like to show you what we're looking for, and I forgot to sketch that on here. So we have velocity, we can say final maybe is what we're looking for. And we'll call, well, that one I don't have to label. Okay, so let's start off with our mechanical energy formula again. So I like to say energy mechanical before is equal to mechanical energy after. Right, you can do ETI, ETF, whatever notation you like. I like this notation. It's just very clear for demonstrating, I think. Okay. Well, what types of energy does this cart have? This cart is 8.6 meters above the ground, so it's going to have some potential energy. It also has an initial velocity. Okay? There's no springs at play though, so we could say that to account for the height, we're going to have some potential energy due to gravity. Initial. We're also going to have some kinetic energy because whenever we have velocity, we have kinetic energy. So energy kinetic initial. Also, I should forewarn you, if you have a small sheet of paper, write small because there's a lot of numbers to move around here. Alright, we also have our after situation. So after is going to be on this side of things. We have some potential energy value. We can say that we have potential energy due to gravity final. We have potential energy because we have height. Okay, and then plus, we're going to kind of assume that if energy is conserved, and this is now lower, it's probably going to be going faster. Because the total amount of energy is the same. If potential energy is less, we're going to have some more kinetic energy, which means we're going faster. So we know we're also going to have some energy kinetic final. Okay. Now comes the big write it all out step. So we're going to have mass times gravity times height initial plus 1/2 mass times velocity squared initial is equal to potential again, mass times gravity times height final plus 1/2 mass times velocity squared final. Okay. Now, like the first example problem, there is no mass to this cart. Thankfully, every single term given has mass. And remember, it only works if every single term has it. Essentially, we're dividing every term by mass. Okay. Good show, we're doing well. I am going to rewrite this formula out again. So now we have gravity times initial height plus 1/2 initial velocity squared is equal to gravity times height final plus 1/2 velocity final squared. Okay. Let's go through and check how many of these things we have and how many of these things we want. So gravity we have, or little g we have, it's acceleration due to gravity. We have the initial height, 8.6 meters. We have initial velocity, 4.5 meters per second. Again, little g. Final height, 5.9 meters. And final velocity. The only thing we're missing, and it's what we're looking for. So I think we can go about solving this. Okay, well, the next two steps for this video are going to be me filling this in with numbers and then jumping to one step before the absolute final solution. So a lot of the calculation work I'm going to skip out just to keep this video a little bit more brief than it would likely be otherwise. So let's fill this in. Let's go, well, I'll stick with blue now. 9.81. Oh, I'm going to have to move this over, otherwise I'll run out of space. 9.81 meters per second squared times height 8.6 meters plus 1/2 VI squared, so that's 4.5 meters per second squared is equal to 9.81 meters per second squared times our final height, 5.9 meters plus 1/2 VF squared. Alright, the rest is solving in algebra. So if you solve these out, you're going to get some value. You can rearrange this over to the other side, and then you can multiply your value by 2 or divide by 1/2, whatever you like. And the value I'm going to leave here is velocity is equal to the square root of 73.224. And when you run that number, we get a final velocity, so maybe I'll put VF here, equal to 8.6 meters per second. So if we didn't quite get that, I'm fairly confident in this answer. Run your algebra again. There is any question that has a large number of values and calculator inputs like this, a very high chance of error. In fact, I would almost say that this area, somewhere in here, oops, that's not the tool I want. This is sort of like a danger zone kind of situation. That said, if your process is right on an exam, I will take almost nothing off for calculator errors. Generally, if your process is totally right and you have some sort of mistake in your error, I'll probably take half of a mark off out of several marks. So, that said, that is the final answer for this question. That's all.